The first beetles arrived quietly, crossing the Rio Grande sometime in the 1890s. They were small, greyish-brown insects, each no larger than a grain of rice, but their hunger was immense. They landed in the cotton fields of southern Texas and began to feed. Their target was the cotton boll itself, the soft white fibre that was the economic lifeblood of the entire region. A farmer would walk his rows at dawn, his fingers brushing the plants. Just days before, the bolls had been swelling, their protective husks tight. Now he found them punctured and weeping a dark, sticky sap. Inside, the tiny weevil larvae had hatched, chewing through the precious cotton lint, turning it into a ruined, soggy mass. The damage spread field by field, a creeping wave of destruction moving east. Panic tightened its grip on the south. This was more than a bad season. It was an existential threat. The weevil reproduced with terrifying speed, and traditional methods, picking them off by hand, burning infected plants, were utterly futile against the advancing millions. In county offices and farmhouse kitchens, the same desperate question echoed. What could stop an enemy this small, this numerous, and this hungry? The desperate search for a solution that began in Texas found its answer in a laboratory. By the 1890s, agricultural chemists had synthesized a new weapon, a fine, white powder called lead arsenate. They promoted it as a miracle, a chemical so potent it could stop the weevil's devastation in its tracks. Word spread through farming communities, carried on the pages of agricultural journals and the promises of traveling salesmen. On a Georgia farm, a farmer hefted a heavy sack, its contents spilling like pale flour into a wooden barrel. He stirred water into the powder, watching it dissolve into a milky slurry. The mixture had no strong odour, nothing to signal its deadliness. He pumped the handle of his sprayer, pressurizing the tank until a fine mist hissed from the nozzle, coating the drooping leaves of his cotton plants in a toxic film. The effect was immediate and brutal. Boll weevils that gnawed on the treated plants ingested the poison. The arsenic disrupted their cellular metabolism, paralyzing their digestive systems. They stopped feeding, curled, and died within hours. The farmer walked his rows, crushing the brittle, blackened bodies of insects under his boots. His crop was saved, and he marked the barrel for refilling, unaware that each application was seeding his land with a persistent metallic legacy. With the white powder proving effective in Georgia, the call for its use grew louder. By the early 1900s, the United States Department of Agriculture had taken up the cause. Their scientists published official bulletins, thin pamphlets filled with precise instructions. Farmers across the South received them, pages detailing exact mixtures of lead arsenate to water and diagrams of hand-pumped sprayers for coating every leaf. The guidance transformed local practice into a national campaign. A farmer in Alabama would follow the government's charts, measuring ounces of poison into his tank. He'd walk the rows, pumping the sprayer's handle until a fine mist settled over his field. This ritual repeated each growing season, from the Carolinas to Texas, as the department's endorsement turned a desperate experiment into standard agricultural doctrine. For decades, the practice continued unabated. Millions of acres received their annual coating. The arsenic did not vanish with the harvest. It lingered in the dust that blew from the fields and in the thin layer of soil where the cotton roots had been. Unknowingly, an entire generation of farmers was building a toxic reservoir into the very land that fed them, following instructions printed in Washington. As the decades passed, the white dust from countless sprayings didn't just vanish. It settled into the earth, a toxic inheritance. Each season's application added another microscopic layer of lead arsenate to the topsoil. The fine particles clung to clay and organic matter, binding tightly as the soil chemistry locked them in place. What had been a surface treatment became a permanent part of the land itself. When farmers eventually moved on from cotton, abandoning exhausted fields or rotating to other dryland crops like soybeans, the arsenic slept. It posed no immediate threat in that dry, oxidized state. The poison was sequestered, trapped within the soil matrix. For years, it lay undisturbed just inches below the surface, a dormant reservoir waiting for a fundamental change in its environment. The transformation was chemical, not visual. No ominous stain marked these fields. To any observer, it was simply dirt, rich, dark southern soil. But locked within its particles was a century's worth of accumulated toxin, a direct result of the agricultural crusade against the boll weevil. The land remembered what the people had forgotten. The cotton era had ended, but the land remembered. In the humid flatlands of Arkansas, a landowner surveyed his property, acres of tired soil that had once produced white bolls. He hired workers to dig drainage ditches, their shovels cutting through earth still laced with the faint, gritty residue of decades-old pesticide. The goal was transformation, to flood these fields and grow rice instead. Pumps hummed day and night, drawing water from the nearby bayou. The dry, cracked earth slowly vanished beneath a shallow, reflective sheet. Where cotton stalks had once stood, green rice seedlings now poked through the water's surface. The landowner watched, satisfied with the conversion, a practical shift to meet new agricultural demands, unaware he was setting a dormant chemical timer in motion. Across the Mississippi Delta, similar conversions unfolded. Former plantations, their soils heavy with history, were re-engineered into intricate networks of levees and paddies. This was not merely a crop change. It was a fundamental alteration of the land's relationship with water. The stage was now set for a quiet chemical unearthing as the new environment began to interact with the old poison. The transformation was complete. Where cotton once stood in dry, sun-baked rows, now shimmered a flooded paddy, its surface a perfect mirror for the southern sky. The landowner who had engineered this shift watched the water settle, unaware that the chemistry beneath his boots was already beginning its silent, irreversible revolution. The soil, once aerated and dry, was now submerged, cut off from the atmosphere above. Oxygen vanished from the submerged earth. In this new, anaerobic world, chemical bonds that had held firm for decades began to fail. The microscopic particles of lead arsenate, locked in the soil since the age of spraying, now found themselves bathed in oxygen-starved water. Their crystalline structures, stable in dry air, started to slowly dissolve. Arsenic atoms began to let go of their lead partners. Freed from the mineral matrix, the arsenic transformed. It became soluble, changing into a form that could travel. It seeped from the dissolving particles, entering the standing water that filled every pore of the soil. This contaminated solution now surrounded the delicate hair-like roots of the young rice plants, presenting the crop with a toxic nutrient it was never meant to absorb. In the flooded quiet of the paddy, the rice plant's roots drank deeply from the water that now held the dissolved arsenic. The toxin, once locked in soil, slipped into the plant's vascular system as easily as a nutrient. It was a silent chemical mimicry. The plant could not distinguish the poison from the sustenance it sought. The arsenic travelled upward, climbing the narrow ladder of the stem. It moved with the plant's own sap, a passenger in the flow that carried water to the leaves and the developing seed heads. In the grain, still soft and milky, the element began to accumulate, molecule by molecule, concentrating within the starchy core. Weeks later, a farmer waded through the same field, the water now drained away. He cut the golden stalks, bundled the harvest, and saw only a healthy crop. There was no stain, no smell, no warning. The transformation was complete. A century-old agricultural poison had been quietly translated into food. The rice from those southern paddies, once harvested and bagged, eventually made its way to a university laboratory in South Carolina. There, in the late 1980s, a soil scientist running routine tests paused. Her spectrometer readings showed arsenic concentrations in local rice samples that didn't match the expected background levels for the region. The numbers were consistently, quietly elevated. Puzzled, she left the hum of the lab and descended into the university archives, a basement room smelling of old paper. She pulled dusty county agricultural ledgers from the shelves, their pages brittle. Cross-referencing her data with historical crop maps, she began plotting points. A pattern emerged. The highest arsenic readings consistently overlapped with areas documented for intensive cotton cultivation decades earlier. The correlation was stark on her desk, illuminated by a single lamp. Parcels of land that had once been drenched in lead arsenate to save cotton were now, generations later, producing rice that carried its chemical ghost. The poison had not vanished, it had merely changed its address, moving from the soil into the food, silently feeding the modern world. That initial discovery in South Carolina sent ripples through the scientific community. By the 1990s, research teams across multiple universities were drilling core samples into the flooded soils of Arkansas and Mississippi. Their analysis revealed a chemical fingerprint in the rice grains, arsenic compounds with a specific molecular structure that matched neither the region's natural geology nor modern agricultural chemicals. The search for the source led chemists to dusty museum collections. They compared their rice samples to archived specimens of century-old lead arsenate powder, preserved in glass jars from the original manufacturers. The isotopic signatures aligned perfectly. The arsenic in the rice was not a new pollutant. It was the weathered, mobilized ghost of those old cotton pesticides, finally revealing its presence after decades of silence. By the 2000s, the pathway was fully mapped. Flooded conditions had dissolved the long-buried poison, allowing rice plants to uptake it. The evidence was now incontrovertible. The elevated arsenic in southern rice traced a direct line back to the lead arsenate sprayed on cotton generations earlier, confirming that an agricultural solution from the 1890s had quietly seeded a problem for the 21st century. The evidence was now irrefutable. The chemical signature in the grains matched the synthetic arsenic from old pesticide formulas, not the mineral arsenic found in bedrock. In her lab, the scientist placed a modern bag of rice from a supermarket shelf next to a century-old photograph of a farmer spraying his cotton. The connection was no longer theoretical, it was physical, sitting in millions of kitchens. This meant the contamination was a legacy, not an ongoing event. The arsenic had been waiting in the soil since the last sprayer fell silent. When those fields were flooded for rice decades later, the poison woke from its dormancy. Each grain harvested carried a minuscule fraction of a historical burden, a quiet consequence of agricultural choices made by different people in a different era. So the story in that bag of rice was not one of modern negligence, but of a long chemical memory. The arsenic present today is the final diluted chapter of a campaign that saved the cotton crop over 100 years ago. It is the afterlife of lead arsenate, a ghost in the grain, persisting as a faint echo of the past in the food of the present.